to fade back in here, unfreeze. And so, let's work an example problem. We are working on getting the pictures down for these example problems. So, let's take a look at this problem right here. Then A has the following eigenstructure. If you were asked to solve this in real life, then what would you do? You'd start work on this matrix. So step one is to figure out eigenvalues and eigenvectors of A. Okay? And so to help us out with that, what I'm going to do is I'm going to move this over here, and then I'm going to, okay, everyone take a look at the matrix 0, 1, -4, -5. You can write that down. You can start figuring out the eigenstructure for that if you'd like, but here, over on board number 2 here, which I'll go to, let's cheat, because I can go to symbolab. I can enter in here, I would like to do an eigenvector problem. Right, and then it says, okay, enter your data for the eigenvectors, and my data is a 0. It is a 1. It is a -4. It is a -5. That would be the first part of the problem, is I would need to identify the eigenvalues and eigenvectors for this matrix. So it tells me if the eigenvalue is -1, one of my eigenvalues is lambda1 equal -1, this corresponding eigenvector V1 is equal to -1 and 1. Okay, there we go. And then I have lambda2 is equal to -4. And the eigenvector for that is going to be V2 is equal to -1 and 4. Okay, so I have pulled up the eigenstructure from this computational tool, and I now have the eigenstructure. And so with that eigenstructure, let's just write down the solution. What do I have? I have 2 eigenvalues. They're real, they're different. And so I should be able to write down my general solution, x of t is equal to C1, eigenvector 1, which is -1, 1, e to the eigenvalue 1, which is e to the -t, plus C2, eigenvector 2, e to the eigenvalue 2t. There's my solution. Okay. So now what we want to do, our main goal right here, isn't the eigenvalue eigenvector problem that was in the past. What I want to do is I want to try to graph this thing. So I have this xy plane cooked up right here. And in this xy plane, what am I going to do? I'm going to identify my eigenvector. My first eigenvector is -1, 1. So that gives me this point right here. I make this vector going through the origin. That is my eigenvector. But that eigenvector has a constant multiple of C1, so any multiple of this vector would then give me this eigenline. So there's my first eigenline. And now, because of this -1 in the exponent on this eigenline, what am I going to do? I'm going to put arrows. In what direction do I put my arrows on this phase line? Do the arrows point into the origin or out from the origin? They point inwards, so I get some arrows pointing inwards. Evidently, this first eigenline is a sinc from our phase line discussions from before. And now here's the lame part. I'm going to have -1 and then 4. 1, 2, 3, 4. I'm going way up here. And so you might notice that the previous examples that I did had eigenlines that were nicely separated, and that's not going to happen here. So I have this -1, 1, 2, 3, 4. Here's my purple vector, and then I get any multiple of this purple vector, so I get a green continuation. So here's my second eigenline, And then how do I want to put my arrows on this second eigenline? Well, I have -4. So my arrows point inwards. I have the intersection of two sinks. What this means is that as time goes to infinity, everything goes in according to the arrow, so everything goes into the origin. And so if I took some notes here, notes, as t goes to infinity, the x vector goes to 0, 0. Okay. But now I have to figure out how this happens. There are two options. Way far back in time, I could be following purple, but then way far forward, I could be following brown. Or way far backwards in time, I could be following brown in terms of a direction parallel, and then at the end of time, I could follow purple in. I've got to decide how that's going to go down. So I'm going to look at t being a very large number, t being much, much greater than 1. Yeah, so the question coming up in chat is, will we ever have to draw these things ourselves? Yeah, that happens. I believe our worksheet will ask us to do this. And if time goes to infinity, both of these exponentials are going to decay, but as time gets really big, which of them are going to decay faster, purple or red? Yeah, purple will decay away faster when time gets really large, so if purple decays away faster when time is really large, your solution is approximately C1, -1, 1, e to the negative t, plus a bit. Right? That's just English language there to say, well, this is still contributing something, so I'm not right on top of brown, but really this brown eigenline is dictating my direction because this little bit of something is small because time has gotten very large, and that -4 right there is going to decay purple away faster. Now, if t is much, much less than -1, so I'm way back in history, now t is much, much less than -1. It's a really big negative number. Both of these exponentials now are blowing up. And since both of these exponentials are blowing up, I ask the question, which one blows up harder? And that would be red or purple. Yeah, that's purple. So now purple's guiding everything way far back in time. And so I get purple plus a little bit. And so let me color code these up. This is purple. And then this here is brown, or red, however you want to color code that. So here's the game. Really far forward into the future, everything is going to be drawn into the to 0, 0. That is the equilibrium solution. Everything wants to go there. There are two guiding lines that get me there, and those are my eigenlines, the purple and the brown. Really far backwards in time, I am behaving most like purple, and really far forwards in time, I'm behaving most like brown. So now I have to draw some trajectories that are behaving like purple really far back in time, and then switch over to the brown behavior before ultimately going to the origin, which is the equilibrium solution. So how is that going to look? Because the angles here are acute, things are getting smushed into these tiny little wedges of the plane, and that's fine, but let's try to get something drawn in that tiny little wedge. Really far forwards in time, I'm brown, so I'm like this eigenline. Really far backwards, I'm purple, so I'm going to come in like purple. And then brown is going to be the line that brings me in. So I do something like that. So let's do the other acute angle. I'm coming in like purple or green, and I'm ending like brown. So I'm coming in like purple, green, I'm ending like brown. I'm going to do one more because it's these small little acute wedges that are easier to draw. So I go in like that. Now what's funkier are these outer edges, or these obtuse wedges. And so I'm coming in like purple. Purple, purple, purple. I'm guided by purple. And then as I get closer to brown, I'm like, what? Brown wants me to do what? Oh, I'm going to have to bend. Bend, 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 bend. Go to the origin. Coming in like purple. I'm seeing brown. Bend, 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 bend. Coming in like purple. I'm seeing brown. Bend, 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 bend. Okay. And there we go. That is the graph that is made, where these eigenlines are my scaffolding guiding solutions, which are represented by styrofoam peanuts flowing in the plane to the origin. For this reason, the origin, which I'll highlight as a red dot right here, the origin is known as a real sink. Why is it a sink? Well, it's the intersection of two sink lines. Why is it, why do I call it real? Because the eigenvalues are real, as opposed to a fake sink. Yep. That contrast will be made more apparent here in a minute. Okay. So over on this other screen, I'm going to get fired up.
Yeah, go ahead.
So when you say when t is much greater than 1, you say that x resembles our first single constant, which is the brown line. So why do we start by following the purple line?
Okay, good question. So really far forward in time, I'm tracking along brown. That's why all of these lines get close to each other as they're following brown into the origin, right? So that's for t much greater than 1. Now, for t much less than -1, so something really far back in history is how we should think about negative time, really far back. Well, then it should behave like purple. So up in here, this is really far backwards in time, and that's a great question, and maybe I can get that question highlighted here. History is t much less than -1. Here is the historical part, deep in the past. Deep in the past. Deep in the past. And now as I go forward in time, there's got to be some sort of switch that moves me from purple in the past to brown in the future. So as these these styrofoam peanuts come jetting in, they will start getting closer to the brown line. And once they realize the brown line, it's starting to take further control. And so that is the future. And that's where all this stuff is coming in. Okay. Does that make sense?
A little bit, yeah. But then can you explain the behavior of the line in the fourth quadrant? That where they start steep with a negative slope and then go towards
Like right here?
No, the fourth quadrant.
Here.
Yeah.
Yeah, so these
because that looks like it's forward in time from my perspective instead of way back in time, and so I'm a little bit confused by that.
Oh, these right here?
Purple line.
Yeah. So
if I tracked them further and further out, which I'm out of space, like go further and further down the paper, green, purple, this second eigenline is what they would be mimicking in terms of being parallel to something. So it seems really, or closer in time, because time is a little bit difficult to perceive in here, but I needed more space down below to graph them further away. Like these guys here are much further away from the origin than these. Does that help?
Yeah, I was getting the x-axis confused with time.
Oh, I see.
Yeah, no, this is kind of cool because we're kind of abstracted from time. We see all time on these graphs, except for further out at spatial infinity. Okay.
So, on this equation, if it was either the positive t, would the brown line be a source instead of a sink?
If this red here was positive,
Yeah.
Yeah, then the brown line would definitely be a source. And then now you have a competition between a source and a sink. Okay, and we'll revisit that in just a second. But what I have cooked up here is the animation. Okay, are we ready for the animation? Camera 4. Styrofoam peanuts in motion. Way back in time, they're following some sort of line that's going through the origin in quadrant 2. And then as they get closer, they start following this line, which has the heavy dominance. That is our brown eigenline. So here we see lines or trajectories that are very much like that line going through quadrant 1 and 4 at a 45-degree angle, and then they get closer to this other eigenline, and they're like, oh, bend back around. Okay, ready? Camera 2. Camera 4. Camera 2. Camera 4. 2 phase lines, both sinks because the eigenvalues are negative, everything going to the origin. Okay, questions? Okay, and so Scott asked a question about if one eigenvalue was positive and one eigenvalue was negative, what would we have? We would have something more like this, which was done right before the break. Here is a source line. Here is a sink line. I'm drawn in on the sink. And then I get closer to this other line and I'm repelled away. And this was called a saddle. So, saddle, eigenvalues are real. One positive, one negative. Sink, eigenvalues are real. Both of them are negative. And then what's the last thing you think you could have here? Eigenvalues are real and they are, instead of negative, both are positive, and we would call that a source. Maybe I can get it cooked up here. Huh? No? Huh? I say boo. Let's see, what would I do here? Maybe this? Ah, there we go. And so now things are being spewed out of the origin. They follow a line on the way out, and then they bend back around to follow another line. Okay. What happens when it reaches the origin? Truth be told, none of those styrofoam peanuts in this case actually ever reach the origin, because it takes infinite amount of time. So it happens in the limit. What happens when they reach the origin? Well, I guess they have a styrofoam peanut positive, or party. Okay. Boop, 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 boop. Let me see, what do we have next? I'm going to leave a note right here. This problem was done in the 4 p.m. class on 11/23. So if you want to check out the work for that, this was done in the 4 p.m. class on 11/23. If I want to go over to this video playlist for planar dynamics, I bet it's a source. Ah, yes, fall 2020, there's a source. And so, yes, you can take a look at this problem. Same sort of game, same sort of arguments. I even bust out the lab there. And so you can take a look. You lay out some guidelines, their sources. You judge which direction they go. Make some arguments. Develop some styrofoam peanut trajectories. And then we look at the visualization. So that can be found in the playlist. What I'd like to do now is move on to another classification.